This question's a linearizing question. So we're told that the colony of bacteria can be modelled by this exponential model, but to make it sort of easier to read and see the information, they've actually plotted it as a linear model, so the exponential has been linearized. So the first thing they want us to do for part A is show how you do that linearizing. So we don't actually need to refer to the graph for this. We need to take this exponential model. So t and y are our variables, and a and k are two constants that we'll be asked to find later in the question. So they've taken logs, and they've specifically taken log to the base 10. So that's our first step. And then it's just using our laws of log. So the left-hand side is already exactly what they wanted. The right-hand side just needs a couple of stages of rearranging. The first is using the law of logs that says if you've got log A plus log B, as long as they're to the same base, that can be written as log to the base of A multiplied by B. So we're going to use that in reverse here and say that if we've got log of k times A to the power of t, I can split that up like that, okay? And then I'm going to be able to use my power law, which says that if you've got a coefficient in front of a log, that can be brought up as a power. So again, I'm going to use that in reverse and basically bring that power of t down as a coefficient. Okay, and then if we look back to what we were trying to prove, we've got everything exactly as they want it. Okay, so now we're asked to find the values of A and K, so we will need to use the graph for this. And if we look, I know it looks slightly more complicated, but actually this is just the equation of a straight line. There's our y, that's our constant, t is our variable, so that's our x. Okay, so that just means that if I compare that to an equation of a straight line, that's my gradient, and that's my y-intercept. Okay, but instead of y, it's log to the base 10 of y, and instead of x, it's the variable t. Okay, so I just need to read the y-intercept and the gradient from the graph. So just want to do this as accurately as you can. So if we do the y-intercept first, that looks to me like it's 0.3. So log to the base 10 of k is 0.3, and then if I take that out of log notation, that would be rewritten as 10 to the power of 0.3 is k. It doesn't mention which form to give it in, so I will get that as a decimal. So 10 to the power of 0.3, and I will give that to 3 significant figures. So that's going to give me, well, that's going to end up being 2.00 if I round that to 3 significant figures. Okay, so then to get the value of m, I need to find the gradient of the graph. So again, I just want to do that as accurately as I can. So do as big a triangle as you can. So I'm going to try and find 2 points where it goes through exact coordinates. So I'm going to use that. So my change in y is going from 0.2 to 0.7. So 0.5. My change in x is going, sorry, there's a bit of a typo there. They should be minuses. So it's going from minus 0.2 to 0.8. So that's going up by 1. So the gradient, change in y over change in x is a half. Okay, looking back to this linearized equation, m is log to the base 10 of a, and we've just worked out that that's 0.5, so a It's 10 to the power of 0.5, so this is going to be the square root of 10. So again, let's grab the calculator. So 10 to the power of 0.5, and again I'll go to three significant figures, so 3.16. And then the final question, this is a really common thing, is to ask you why the model may not be valid over a long period of time. So I would always start my answer by saying that. So, because obviously any model is not going to be accurate forever and ever and ever. So the model will not be accurate for a long period of time. Then just try and give a reason, or you could come up with a couple that's related to the situation they've described. So this is about a colony of bacteria growing in a lab. So just how you don't need an expert knowledge of the situation, but just think about what might limit the growth of these bacteria, and the petri dish, or whatever they're being measured in. So there may be limited space, which means the number of bacteria, sorry, not really mentioning the number of bacteria, it's just the size. So let's use the same words that they use. So there may be limited space, which would limit the size the bacteria can grow to. There's going to be other things as well. I mean, you may have a more in-depth knowledge of this than me, so anything else that you can think of, that just a sensible reason as to why that model is not, the bacteria is not going to continue increasing at that rate forevermore.